Hey smart people, Joe here, and here too. I'll explain the clone later, but we are really excited today to share with you a new YouTube feature that lets us watch the video along with you in real time. So let me get this synced up here, and what am I looking at? When does this happen in the video? Now. You're looking at now. Everything that happens now is happening now. What happened to then? We passed then. When? Just now. We're at now. Go back to then. When? Now. I can't. Why? You missed it. When? Just now. When will then be now? Soon. When is now? When is now? Now, for you, as you watch this video, is whatever time and date it is, wherever you are at this moment. But that's different from now for me as I make this video. I mean, my now is at some point in the past compared to your now. But whose now is the real now? Okay, I mean, obviously I'm in the past compared to you now, right? I made this video, I uploaded it on that date, but I can't access your future. For me, now is right here, in this moment. Okay, maybe this is all just semantics, we're just arguing over words. I mean, if I was right there in the room with you, surely then we'd be able to agree on the same now, right? But what if I was on Proxima b? Proxima b is the nearest potentially habitable exoplanet, a little over 4 light years away from Earth. Let's pretend for a moment that you have an incredibly powerful telescope capable of seeing me in my little space cabin on the surface of that planet. What am I doing right now on Proxima b? Well, there's no way that you could know. Because of the speed and travel time of light, you can only ever know what I was doing 4 years ago. Whatever you think of as now on my distant planet is in your future. For all you know, a black hole opened up and swallowed me and my little planet, and I'm not even there anymore. The point is, and what I'm going to show you, is that according to the laws of physics and even neuroscience, the now you experience is yours alone, and it depends on where you are and what you are or aren't doing. In 1971, scientists loaded atomic clocks on board commercial airplanes. These clocks flew twice around the world, once eastward and once westward. Afterwards, the time that they recorded was compared with clocks that had remained stationary, and the 3 sets of clocks no longer agreed. They didn't malfunction. If you were sitting next to that atomic clock on the plane, it worked perfectly. They had all kept time correctly. But because they had moved relative to each other, they no longer agreed on when was now. And these differences were precisely consistent with Einstein's predictions of special and general relativity. Now, general relativity deals with how clocks tick faster or slower depending on the strength of gravitational fields. Closer to Earth's center, in a higher gravitational field, all processes, including clocks, are slower. General relativity predicts clocks at higher altitude tick faster than clocks on Earth's surface. And that's exactly what they observed. But it's the predictions of special relativity that are perhaps more mind-blowing. Movement also slows time, at least from the point of view of someone standing still. The clock that flew eastward, effectively moving faster than the clock on Earth, ran more slowly. The clock that flew westward, effectively moving slower than the clock on Earth, ran faster. Or another way to look at that is from the westward clock's point of view, both of the other clocks are moving away from you, and both run more slowly. These differences were only on the scale of nanoseconds, billionths of a second, but they were measurable. And today, calculations using GPS satellites take these effects into account. And it gets even weirder. Not only can 2 clocks disagree about when is now, 2 people might not be able to agree on the same now either. Imagine 2 observers, one in the center of a speeding train and the other standing next to the train as it goes by. I don't know, Doc. That's bad, Marty. As the center of the train passes this observer, 2 bolts of lightning strike at the front and the rear of the train. Now, the flashes of light from each strike reach him on the ground at the same time. So he concludes that the strikes were simultaneous. I mean, obviously, right? We know that the light from both strikes traveled the same distance to his eyes at the same speed, the speed of light. But what does his friend on the train see? From his perspective, the train is moving to meet the front flash and away from the rear flash. The light from the front flash hits him before the light from the rear flash catches up, and they draw a very different conclusion from the person on the ground. The front flash happened first. This happens because of one important rule. No matter if we're on the ground or on the train, the speed of light does not change. It is universal everywhere from any point of view. From the perspective of the person on the train, each pulse of light traveled the same distance from either end of the train. So if the passenger sees one flash before the other, they can only conclude that the front flash happened before the rear flash. Our two observers disagree about the order of events and whether two events were, in fact, simultaneous. Their nows don't match up. So whose interpretation is correct? Well, what Einstein showed with special relativity is that they're both correct in their own reference frames. From different reference frames moving relative to one another, there can never be agreement on the simultaneity of events, what we call the relativity of simultaneity. Now let's look at that train from a different perspective. This time, the passenger at the center of the train takes a photo just as the train passes our observer on the ground. The light from that flash reaches each end of the train simultaneously. But our friend on the ground, from their perspective, the back of the train is moving to catch up with the light from the flash. But on the other side, that light has to catch up with the front of the train. From the perspective on the ground, the light strikes the front of the train last. Again, our two observers don't agree on what is simultaneous, and they are both right in their own reference frame. If we are moving relative to each other from your frame of reference, there will be a moment where two events are simultaneous. And from my reference frame, there will be a moment where A and B are not simultaneous. And if we can't agree on what is simultaneous, we can't agree on now.
Marty, now doesn't exist.
Are we good? But hopefully we can agree on one thing. Tacos are delicious. Get out of my belly. Let's say you and I want to meet for tacos. I tell you to meet me at my favorite taco stand at 12 noon. I have to tell you where to be, the taco stand, and when to be, noon. I have to give you a set of coordinates, not only in space, but also in time. I mean, the coordinates in space alone are not enough. I mean, you could show up at a different time than me. And the time isn't enough either. You could show up anywhere. We can only share our delicious taco moment if we describe both space and time. Imagine it this way. Since most of us are stuck to Earth's surface, we can tell where we are with just two coordinates. And we can watch as these coordinates change along a third axis, time. All of this together is space-time. Now, technically, there are three coordinates of space and time is a fourth dimension, but unfortunately that's a little hard to illustrate in this pesky three-dimensional universe. We think of reality as one of these moments in time. And if you and I exist in the same reality, which I'm pretty sure we do, then we must exist in the same moment in time. There must be one moment that we can agree on as now, right? Our everyday experience tells us that the three-dimensional universe at this point in time is what is real. The past and future, they aren't real in the same way as the present. I mean, sure, we can remember the past and we can predict the future, or we can imagine it, but we can't go to either of them. And whatever we're remembering about the past or predicting about the future, we're really just doing that with our brain now in this moment. This way of thinking about the universe is called presentism, that the present is what is most real. And this way of thinking might be wrong. One of the beautiful things about the laws of physics and the equations that describe them is that they work equally well here or in another galaxy. And they also work equally well 1,000,000 years from now or 1,000 years in the past. There's nothing in the laws of physics that makes now particularly special. Those laws of physics also lead us to some weird conclusions. If I knew everything about the universe right now, every particle, every motion, and every bit of data, I could predict what will happen next everywhere. And and I would be an all-powerful god. Sorry, I drifted away for a moment. With this information, I could also reconstruct everything in the past. Past, present, and future moments are all connected through the laws of physics. This is a view called eternalism. Imagine stepping outside of the universe to view it as a single block of all moments and all spaces. This is what some have called the view from no-win. This view says that all moments are equally real, and there's nothing special about the present moment except that you are experiencing it right now. That doesn't really fit in with our everyday experience of time and space, but it seems to be a logical consequence of physics. So what is real? Physicist Sean Carroll puts it like this: all moments in time are real, but some we understand better than others. Speaking of understanding, to understand something, we need to observe it. And we observe things using light. Imagine a flash of light in space. A second later, that light pulse has created a sphere 1 light second across. And every second after that, that sphere will continue to expand. In two-dimensional space, our expanding sphere will appear as an enlarging circle, tracing the shape of a cone as it moves forward in time. This cone represents everything this light will ever touch, expanding into space at the fastest speed there is. That means someone here could never see it. We can only see it if we are here inside the cone. Likewise, from any point, the mirror image cone extending down represents all light, how old and how far away that could ever reach us from the past. From any event, light and information advance outward in every direction as time progresses upward, forming an ever-enlarging circle throughout all future moments. Our past light cone is everywhere and every win we can see in the past universe. Our future light cone is everywhere and every win we could ever communicate with or travel to in the future. We can't interact with or see or even know about anything outside of our own light cone. There are moments in time and space that may be real, just not to us. This is your absolute elsewhere, or perhaps we should say else when. Moments here are neither past nor future nor present. If you're feeling a little disoriented right now after realizing that now doesn't exist out in the universe, well, don't worry, it gets weirder. Now might not even exist inside your own brain. How did I do that? When we see a ball or anything, it takes 10 to 50 milliseconds for information from the eye to reach the brain, and another 100 or so milliseconds before we can take actions on the basis of that information. During that time, the ball continues to move. So it seems like the brain's information about where the ball is will always lag behind where the ball actually is. So how are we able to catch the ball? Well, maybe our brains guess ahead where the ball will be. Maybe we use the information from the past to predict the present. Well, it's not quite as simple as that at all. Keep your eyes focused on the X. As the ring moves, a white circle flashes. What most people perceive is that the flash lags slightly behind the ring. But if we freeze at the instant of the flash, the white circle is actually completely inside of the ring. This is the flash lag illusion. Why does our brain see this? Well, thinking back to catching a ball, it fits with what we might expect, that our brain is predicting where it thinks the ring will be, that we are living in the past and our brain is guessing ahead. But this isn't what's happening. Psychologist David Eagleman set up a modified version of this experiment. Everything leading up to and including the flash is the same, but what happens after the flash changes. The ring either continues around, stops, or reverses. And here is what people see. Again, everything leading up to the flash is the same as the original experiment. If we were really using the past motion of the ring to predict its future motion, we'd expect the same result as our original experiment. Our brain's putting the ring ahead of the flash. But that isn't what we see. What we perceive at the moment of the flash depends on what happens in the future of the flash. This is really strange. It means that the moment our brain calls now depends on information from the future. You know, this is starting to sound like we're time travelers or something. A better way to look at it is that there is physical time out in the world, and there's time that we make up in our brains. And when something happens on each timeline, doesn't match. Out in the world, an event occurs, then some other stuff happens shortly after it. Our brains take the stuff that happened just after and combine it with the event itself to create a single moment in our heads, a now that doesn't exist in the real world. It's what Eagleman calls the illusory present. So in a very real way, we do live in the past. When this moment, when now occurs, it's already happened. For experiences like the flash lag illusion, each of us lives in our own now that is 80 to 100 milliseconds in the past of the now in the universe outside our skulls. But why does this happen? Well, because the brain is surprisingly slow at processing information that comes in. I mean, different signals arrive at the brain at different speeds and different times, and they have to be decoded and processed in different regions of the brain before we can have a conscious experience. You see the world a lot like Saturday Night Live. I mean, it seems like what we're seeing is now, but really there's a delay built into what we can see. Only it's not in case someone says a bad word or has a wardrobe malfunction. It's because of all the information from different senses and places reaching our brain at different times. And our brain having to decide which bits of that information happened at the same time. I mean, it feels like all of our senses across our body are unified. That what we hear and what we feel and what we see are all in sync. But this is a feeling created in our brain. And there's a really simple way to demonstrate this. Just touch your nose and touch your foot at the same time. I mean, I feel those as simultaneous, but I mean, the signal from my foot took many milliseconds longer to reach my brain than the signal from my nose just by the sheer distance. But your brain waits and takes all of these signals arriving from the past and like a video editor, syncs them up and creates a conscious experience where they happen simultaneously. This also means that tall people like me live farther in the past than short people. Scientists once tested sprinters to see if the sound from a starter pistol or a flash of light would get them off the line faster. I mean, light travels more quickly than sound, so you would expect a flash works better. But they were actually faster in response to the sound because auditory signals are processed faster than visual signals in our brain. But if that's the case, I mean, why does that work? I mean, the movement of my hands and the sound appear synced, even though the hearing part of my brain gets the signal before the seeing part of my brain. In the early days of TV broadcasting, engineers were worried about how to keep the sound and picture in sync. You see, unlike film, where the soundtrack is physically linked and printed on the film strip, TV broadcasts use separate signals for sound and picture. And it turned out they didn't need to be in sync, at least not perfectly. As long as the sound and picture weren't more than 80 milliseconds out of sync, people's brains made the correction for them, just like yours have been doing. The sound and picture have been out of sync for the last several seconds, and I bet you didn't even notice. But if I walk away at a certain distance, your brain decides the sight and sound are out of sync. That distance is about 100 feet or 30 meters. Because it's the distance at which the speed of light and the speed of sound reach you more than 80 milliseconds apart. Here's another weirdness. Our eyes make small jumps several times a second, movements called saccades. If you stand close to a mirror and look back and forth between your right and left eye, someone watching you will see your eyes move back and forth, but you won't. Our visual system just turns off when our eyes jump from spot to spot. Otherwise, the world would just look constantly blurry. But we never notice these gaps in time because our brain uses the past to fill in the now. You should try this. It's seriously trippy. Your brain is not a clock that tracks time. Time is actively constructed by the brain. And whether it's in our brains or out in space, now is not a place, because time is not a map with coordinates that we all agree on. Time is just a way to measure change, and change can happen at very different speeds for any two people. There's nothing in the laws of physics or even our own brains that says there is one single now. I mean, the universe is a stranger place than most of us realize. Thanks for joining me in this moment, whenever it is, to learn a bit more about it. Stay curious.